This is Shane Picard with a geometry lesson on proving triangles similar. In past lessons, we've looked at proving triangles congruent. Now we want to try and figure out if there are rules that will allow us to determine that they're similar. You may remember that in prior lessons, we started out by saying that in order to prove triangles congruent, we needed to know that all three sides were congruent in all three angles. And from there, we began to whittle things down until we eventually reduced it down to some rules. And just with a few pieces of information, for instance, angle, side angle, or side angle, side, we were able to determine congruence. We'll do the same thing here in the similarity context. We want to whittle it down. We don't want to have to look at all 6 pieces of information. We're simply asking the question, can we do with fewer pieces of information? The first postulate we'll look at is called the angle-angle similarity postulate. Notice that I've highlighted the word similarity in red. We've already talked about a lot of congruence postulates, and it's really important as we move through these similarity rules to keep in mind that the rules for similarity are different than the rules for congruence. A lot of them have the same names. We need to be very careful about keeping them distinct in our minds. So this first one again is called the angle-angle similarity postulate. It states if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. Remember, we've looked at a rule already that tells us that if 2 angles in one triangle are congruent to 2 angles in another triangle, then the third angles are also congruent. It's called the third angle theorem. And so, interestingly enough, we don't have something called the angle-angle-angle similarity postulate because we don't need it. As soon as we know that 2 angles are congruent, we know that all 3 angles are in fact congruent. So let's see if we can apply this rule. We have here 2 triangles, FEG and triangle MLN. And the question is, are they similar? More particularly on the screen, you may see it says explain why they are similar. So there's already sort of a hint given there that they are. Why are they similar? Well, in order to answer the question, we have to discern, in this context, whether there are 2 angles that are congruent. We immediately notice the angles that have measure 102. So we've got angle. So far we have angle. The question, of course, is do we have angle-angle? Well, in order to find the third angles in either of these triangles, we need to use the triangle-angle sum theorem. You know that the sum of the interior angles of a triangle is 180 degrees. So we have 102 on the triangle on the right, plus 48, plus the measure of angle M is equal to 180. And so here we have 150 plus the measure of angle M equals 180. And therefore the measure of angle M equals 30. So we know that's 30 degrees. And already you can see, since this is 30 and this is 30, we have angle-angle. What does that mean? It means those 2 triangles are in fact similar triangles. Pretty easy, pretty straightforward application of the rule. All we need to identify is the fact that 2 angles are congruent, and we know for certain that the triangles are similar. We could ask a different but related question, are the triangles congruent? The answer to that question is I have no idea. I don't know. I don't know anything about their sizes. All I know is that they're the same shape. We could ask the next question, which is, do we have enough information to find the similarity ratio? Do we know the similarity ratio between these 2 triangles one way or the other? The answer is no. And the reason for that is because we don't have the lengths of any sides. If we knew the lengths of any of the sides, that is, corresponding sides, we could very easily identify the similarity ratio. But we don't have that information, so the answer is no. In other circumstances, maybe we do know the lengths of some of the sides. And so oftentimes we can apply the angle-angle similarity postulate to find the lengths of sides in similar triangles. So let's start by asking the question here, are the triangles similar? Are these 2 triangles similar? That's the first question we need to answer. Because if they're not similar, then there's no point in trying to determine the proportions. We have 2 parallel lines, AE and CD, and we have some transversals that intersect those lines. And we know that when we have a transversal intersecting parallel lines, alternate interior angles are congruent, so that means this angle is congruent to this one. It also means this angle D is congruent to this angle A. And right there we have angle-angle already. Hopefully you notice the fact that we have vertical angles here in the center, so those are congruent as well. So we actually have angle-angle-angle, but all we need is angle-angle. Question, are they similar triangles? Answer, yes, by the angle-angle similarity postulate, they are similar triangles. Therefore, we know the sides, corresponding sides, are proportional. So we can begin to build a proportion here. The only thing we need to be careful about is we need to make sure we grab corresponding sides. The next question, or the next statement, says find BC. We want to know what BC is. What's the length of segment BC? How do we find it? Well, all we need to do is compare corresponding values on the sides and build a proportion. So 12 corresponds to 18. 12 is to 18. As 14 in the small triangle corresponds to BC. That's our unknown value, BC. So before we do our cross multiplication, we might as well simplify. 12 over 18 is the same as 2 over 3. And so now we're in a position to cross multiply. 2 times BC is equal to 3 times 14. One of the things I like to do, I like to divide by my coefficient over here before I simplify this product. I'll divide by 2 on both sides before I actually multiply 3 times 14. I just find that's easier because 14 divided by 2, of course, is 7, and 7 times 3 is 21. You don't have to deal with the numbers that are as large. So BC equals 21. We find that with the proportion based on the similarity that we determined by reference to the angles. What are some other ways we can apply angle-angle similarity? But you can use similar triangles and measurements to find distances that are otherwise difficult to measure. This is called indirect measurement. In other words, maybe there are situations in which you can't just take out a tape measure or a meter stick and measure something, and the question becomes, can we find a different way to measure? Yeah, we can use indirect measurement. One classic problem involves the height of a flagpole. Oh, here's the problem. The person who is 5 feet 6 inches measures the length of their shadow and records it as 3 feet 9 inches. So we have a person, forgive my drawing skills, and the person is 5 feet 6 inches. That's this height here. And their shadow on the ground, wow, is 3 feet 9 inches. They also measure the length of the flagpole shadow. So we have a flagpole, and it has a shadow. And they measure the shadow, and the shadow is 16 feet 8 inches. Now, this entire problem depends on one very important factor, and that is we are assuming that as the sun shines down on these two objects, on the person and on the flagpole, that it is doing so at the same angle. In other words, that these rays of the sun are cast at the same angle. As long as that is true, we will actually have a situation in which angle-angle applies. Why is that? Well, if we use line segments to represent the person and its shadow, and the flagpole and its shadow, and we draw in the rays of the sun coming across here, you can see because the rays are presumed to be at the same angle, and the person is presumed to be standing upright, that is vertically, and the flagpole is presumed to be vertical, you can see we have by angle-angle, we have similar triangles. So since we know the lengths of these two sides and the length of this side here, we can find the length of that side. So let's go ahead and set up that proportion. We'll compare the person's shadow length, 3 feet 9 inches, to the shadow of the flagpole, 16 feet 8 inches. And we'll set that ratio equal to the height of the person, 5 feet 6 inches, divided by the height of the flagpole, which we'll call x. Now, we need to cross multiply in order to solve this proportion, but before we do that, there's one thing that would really make a lot of sense, and it's a step that's made necessary by the measurement system we use here in the United States. And what I'm talking about is the fact that it would really be convenient to go ahead and change these measurements either into inches or into feet, but not feet and inches. Those don't work very well together in math. So let's go ahead and change them into inches. 3 feet is 36 inches, plus 9 inches gives us 45 inches. We need to divide that by 16 feet 8 inches. Well, we need to multiply 16 feet by 12 inches per foot. We know that if it were 10 inches per foot, that would give us 160 inches. And 2 times 16 is 32. So we get 192 inches. We need to add the 8 inches to that, gives us 200 inches even. Okay. On the right side, we have 5 feet, which is 60 inches, and 6 more inches is 66 inches. And we divide that by x. Now we need to cross multiply. So before we do that, we might as well reduce this fraction down. 45 divided by 200, you can probably see there's a common factor of 5 in there. So it becomes 9 over 40. Therefore, 9 over 40 equals 66 over x. So we'll cross multiply at this point. 9 times x is 9x, and that's equal to 40 times 66. At that point, we can begin to simplify. Divide both sides by 9. Divide both sides by 9. You can see there's a common factor of 3 in here. 3 goes into 66 22 times. And it goes into 9 once. I'm sorry, and it goes into 9 3 times. So we can reduce those. And now we have 22 times 40 divided by 3. Now this is a good opportunity to grab your calculator, or if you'd like to exercise your ability to deal with decimal values, that'd be fine as well. You can probably see that 3 goes into 22 7 1/3 times, and 7 1/3 times 40. It looks like it's, let's see, 4 times 7 is 28, so that's 280, plus 1/3 of 40, which is actually 13.3, I believe, if I'm not mistaken. So this is 293.3 rounded. Okay, that's inches. Are we done? Well, we're done in a technical sense. We could answer and say, well, the flagpole is 293.3 inches. The next step would probably be to divide that by 12, so we can answer back in feet again. So 12 goes into 293. Well, 12 goes into 29 2 times, with a remainder of 5. That gives us 53. And 12 goes into 53 4 times. Right? 12 times 4 is 48, with a remainder of 5, 53 again. So it goes into that 4 times, and you can see that that would just repeat. So we say 24.4 feet would probably be a good answer. And we can actually lose that last 4 because we're just rounding. What we have is an answer. 24.4 feet is the height of the flagpole. By the way, you might want to check my math. I just sort of ran through it real quick. Make sure that I didn't make any mistakes in there. Let's look at one more problem. The next type of angle similarity application, which is also fairly common, is the indirect measurement, which is used to determine the height of a tree. A lot of times, if people are cutting trees down, they want to answer the very important question, will the tree hit my house, or will the tree crush my shed? Okay, those are important questions to ask before you cut a tree down, aside from all of the other safety-related questions that you want to be aware of. One of the things that's really important to know in order to figure out if the tree will land on your house is how long is the tree. Now, a lot of times when this method is used, you don't end up actually knowing the height or the length of the tree, but you do know whether it's going to fit in your yard. In other words, you know when the tree falls over, you know where the tip of it will be. And that's really the issue a lot of times. Here's the process. First of all, in order to complete this task, you will need a small straight stick. Now, when I say small, I'm talking about the diameter. Probably 1/4 of an inch around, something pretty small, nothing large. And when I say, small, I don't mean small in length. I don't mean short. It needs to be probably about 36 inches, maybe 3 feet. So a stick that's about 3 feet by 1/4 inch. And it needs to be fairly straight. The truth is, it doesn't have to be perfectly straight. You can actually work with a stick that's a little bit curved, but it's much easier if the stick is straight. All right, here are the steps we need to follow. Number 1, stand where you can see the notch cut in the tree. I've drawn a little notch on a piece of paper, a post-it note, which I've placed on my wall. So you can see that I'm standing in a way that I can actually see that notch. By the way, let me just mention the way that you cut a tree. Let me just draw that out real quick. The way that you drop a tree to cut it, which we call felling a tree, is you have the tree here, and you cut a notch in the side of the tree like this. So it would actually look like this at this point. Got the notch cut in it. And then you take the saw on the other side and you cut right here up to the notch. You leave a little piece of wood in there. That piece of wood is called the hinge. And once you do that, assuming the tree has a slight lean to it, the tree will actually fall this way. Hopefully you can see that. So this notch allows the tree to fall in this direction. So that's what we're talking about when we talk about the notch. What's the next step? Step number 2 is to hold the stick and raise your hand so that your fingers are in line with one eye and the notch. So a straight line should go between your eye to your fingers to the notch. Third step is to tilt the stick back toward your eye Slide it forward or back so that it just reaches your eye. Please be careful. Don't poke yourself in the eye with the stick. You need to slide it back so it just about touches your eyeball. Step number 4, rotate the stick into the vertical position without moving your hand. Keep your hand stationary and rotate the stick upright like this. So it should be horizontal. You're going to rotate it upward. Number 5, walk forward or backward until the stick is in line with your eye and the top of the tree. So if you've got the tree here, you're going to move forward and back until your eyeball and the tip of the stick and the top of the tree are all in a line. When I've drawn this diagram here, you can see that this line goes above the top of the tree. So I need to walk in this direction with the stick and my eyeball, of course, so that when I look up at the top of the stick, I need to keep walking here. When I look up at the top of the stick, it just catches the top of the tree. Okay? Once we've done that, we know the place we're standing is the place that the tip of the tree will end up when the tree falls. Let's just answer the question, why? Why is that? Why would I anticipate the tree will land there? Showing this in a diagram, we have an eyeball. Hello. We have a stick. And we have a tree. And if you look at the triangles involved, here they are. There are 2 triangles there. Here's one. I'll label it triangle A, B, C. And we'll label this other one A, D, E. Now, you may remember that in the steps of this exercise, we tilted the stick up and down. At one point, the stick went from our hand to our eyeball. At another point, the stick went from our hand up to this hypotenuse of the larger triangle. And so we know for sure, because it's the same stick, that this segment is congruent to this segment, which means this is a 45-45-90 triangle. So this is a right angle because it was horizontal and now it's vertical. And these are 2 legs of an isosceles triangle. Since we're looking up across this point to the top of the tree, this is still a 45-degree angle. This is a 90-degree angle, assuming, which we are at this point, that the tree grows straight up and down. So because we have angle, angle, the 2 triangles are similar, which means they have exactly the same shape. Well, if the 2 triangles are similar and have the same shape, that means segment BC must be congruent to segment AC, because the shape of these triangles is a right isosceles triangle, which means the height of the tree, BC, is congruent to or the same as the distance that I'm now standing from the base of the tree. So when I cut the tree down, point B should come down by point A, and I should know that the tree hasn't just crushed my shed. Give that some thought, think through it, maybe practice a few times, see if you can get the hang of it. Just give you a couple pointers. You are ignoring the distance from the floor to your hand, and that's important. What that means is when you actually sight in on a tree out in the field or in your backyard, you need to try and cut the notch at the same height as your eye, as opposed to cutting the notch down by your feet. Think through that carefully, and as always, if you have any questions, just shoot me an email.